today we're gonna work through polar coordinates and polar graphs. That's the only section that shows up on the next quiz. And then the following we'll talk about area and arc length and all that kind of stuff with polar curves. So this is 10.4 is going to be all we do this week, and it includes a couple of things. Okay, everybody good? All right. Now, in general, we talk about we've always learned coordinates rectangularly with x and y. Okay. So the first big jump for you guys is going to be we are now going to write a coordinate pair as r theta, where r is a radius and theta is an angle. Okay, so as we think through, where is the point where the radius is equal to 3 and the angle is equal to pi over 2? Well, let's start with the pi over 2. Where would pi over 2 be? It would be on the y-axis. The radius being 3 would be at the point 0,3 then, yes? Everybody good? So that's point A. So where would the point 2 negative pi over 4 be?
Or 5 pi over 4.
7 pi over 4.
Yeah, in between the
Yes.
Third quadrant, radius of 2. Is everybody with me? Because this is negative pi over 4. Would just be going in the other direction. And as we've done many, many times at this point, 2 negative pi over 4 is equivalent to 2 7 pi over 4. Right? And this will kind of trip you out maybe. Negative 2 3 pi over 4. So if my angle is 3 pi over 4, I'm here, the negative radius would go in the opposite direction. Are we okay so far? All right. Now, what are the coordinates of this point then? What are some possible sets of coordinates for that point? 4 pi, 5 pi over 3. What else?
Negative 5, 2 pi over 3.
Negative 4, 2 pi over 3. For negative pi over 3. And there are times, depending on what you're doing, that relating to the space that something takes up makes more sense to use this way of describing where they are instead of, especially in a three-dimensional world. Yes?
I'm confused on how we're getting the negative 4 for the radius. Like, how do you have a negative radius?
So 2 pi over 3 is here, right? So this would be positive radius because I'm going in the positive direction. And so, like, yeah. So the positive radius starts here and rotates this way, yes? Yeah. Okay. So the negative radius would be, I do that rotation, but I'm going in the opposite direction.
Okay, so how do we have 4, positive 4 and negative 4 as possible?
Because when my angle is up here, this would be a negative radius, right? Because it's the opposite direction. But when we were at, say, negative pi over 3, my angle's here. That's the positive direction because my angle's going to hit it.
Okay.
It's only, so for this point, the radius would be negative if my angle is right here, and positive if my angle's down here. They're not, like down here, down here are not the same angle. All right, now, so now that we've kind of just defined like what polar coordinates are, I wanted to talk about how to go back and forth between polar coordinates and rectangular coordinates. And it all is going to stem back to this picture, which theoretically should be incredibly comfortable for you guys by now. Is everybody with me? Okay, so if I wanted to change this from polar to rectangular, like if I'm trying to find this coordinate right here, are you guys with me that that would be equivalent to r, like, well, I know cosine of my angle is equal to x over r. And sine of my angle is equal to y over r. So if I want to find the x coordinate, I just do r times the cosine of whatever the angle is. And if I want to find my y coordinate, I just do r times the sine of what my angle is. So here we have a polar coordinate. Now, just for practice, where would 2 pi be?
It'd be on the
It would be on
x-axis.
the x-axis, on the positive side, negative side,
Negative side.
negative side. So this is my rotation. Is everybody with me? So it'd be right here where this distance is 2. Okay, so you guys, rectangular coordinates, what are they of that point?
0, -2. Right.
Now, if I wanted to use like the general trend that we always do, the x is equal to r times cosine of theta. In this case, that would be 2 times the cosine of pi. The cosine of pi is -1. We get -2. Let's look at another one.
Should we clarify theirs in degrees?
No, because these angles are all in radians still, yes? Cos. All right, so where would square root 3 pi over 6 be?
First quadrant.
In the first quadrant, right? Pi over 6 would be here-ish, yeah? So this angle is pi over 6. My radius is square root 3. So one way we could think through this is essentially, this is x, this is y. We could use sine, cosine, and tangent, or sine and cosine to find them, right? Like, we could say the sine of pi over 6 is equal to y over square root 3. If we needed to. Like, you could draw this out. Like 3 halves and then square root 3 over 2. So you guys got All right, now, what if I have the rectangular point, -1, +1? That would be second quadrant, yes? So this would be kind of my picture, where each of these is 1.
It all goes back to trig.
It all goes back to trig. This is very trig heavy, for sure. Does the picture make sense? Okay, so you guys, what's this angle? The reference angle.
3 pi over 2.
Oh, yeah.
Over
Not
what?
2, over 4.
4. Yeah, to get from here to here. 3 pi over 4. Yes? What's the radius?
Square root of 2.
Now, how did you know this was pi over 4?
Unit circle.
Essentially, yeah. If you knew that's where the tangent is equal to 1. So another way of thinking of it, though, guys, is that the tangent of that angle is going to equal y over x. Yeah? And so if it's not obvious what the angle is, so you can find theta by doing the tangent inverse of y over x. And that'll help you find that as well. And so square root 2 pi 3 pi over 4, boom, I've got my angle. Everybody good? What's R?
2.
What's theta? Done. All right. All right. So next what we're going to start looking at is what happens when you graph polar equations. Okay. So polar equations are usually of the form r of theta equals and then something times theta. So it could be some expression using theta. But we usually write them r in terms of theta. Okay. Just like when we graph lines, or when we graph in the rectangular plane, we have the input, we get our output, and that's how you learned it, right? So that's how we're going to start learning these. We're going to spend a decent amount of time on just graphing these because they are, like, it'll make the next week's stuff, which is the hardest stuff, I think, some of the hardest stuff we'll do all year. Okay? It'll make that much easier once you're way more familiar with the graph. So I'm choosing to take some extra days of just practicing graphing these. Okay? All right, you guys. So consider like when we graph on the coordinate plane, right, on the XY rectangular plane, typical equations are y in terms of x, right? They have x's and y's in them. But then, like, if I have x equals 2, that was the special circumstance of a vertical line, right? Or y equals 5 is a special circumstance of a horizontal line. So what do those special circumstances look like when what we are graphing is r equals 2, where there's no theta in it? Where are all the points where the radius is equal to 2? It's just a circle, right? Here's a radius 2, here's a radius 2, here's a radius 2, etc. Okay. Now, what about theta equals pi over 3? All the angles where no matter what the radius is, it'll be a line at pi over 3. And it can go negative because you could have a negative radius, yeah? All right, so now what happens when it is a function of theta? Okay, we're gonna work these together. I don't want you to stress about this. Okay, like I said, we're spending a lot of time on this, a lot. Okay, you guys, let's start with, you have theta, we fill in a table. So, if r is equal to the sine of theta, what is the sine of 0?
0.
What's the sine of pi over 6?
1/2.
Square root 3 over 2, yeah? Pi over 2 is 1. 2 pi over 3 is square root 3 over 2. You guys, I missed the 5 pi over 6 in the middle, so I'm going to add it on the end. Okay, so now let's graph those points. 0, 0. Then what? Pi over 6 1/2 would be right here.
We don't have the
It's
same
either
little
lines.
lines.
Oh, they didn't copy?
We just have like the
We
bullseye
have-
circles radiating.
And they're really faint.
Sorry, guys.
Big green.
Sorry.
It's gonna be a line.
No.
Okay, so where, you guys, square root 3 over 2 as a quick reminder is 0.866. If that's helpful. So that would be, I don't know, maybe here?
This would be a funky thing.
And then pi over 2, 1. Right?
Oh,
I think these end up looking really cool,
it's like a
personally.
spiral instead.
Is it a spiral?
Maybe.
No, it isn't. It's like a
Because it's going right back down.
Oh, what?
mushroom shape.
Interesting. Never mind.
Or it's just a circle. That ain't a circle.
That does not look like a circle.
Is it supposed to be a circle?
I don't think so.
Mine's looking like the Grinch's head.
I don't know what mine look like.
And just like your calculator had a parametric mode, it also has polar mode, so we can check our answer, see how we're doing. Okay, so y equals, I'm going to notice that it immediately changes my variables to r and theta.
What should the window be?
That's crazy. Do the windows throw me off?
So the window is very similar, where we have theta in between 0 and 2 pi. Yeah.
This one is just the messed up because it's showing like
Oh, my window just ain't right.
the window ain't right.
So I'm going from 0 to 2 pi with, let's go ahead and do negative 2, or x min negative 2. Y min negative 2, y min positive 2.
Wait, why
It only
minus
gives me
positive?
6 options.
Y min,
How do you do auto on the theta step?
I have no idea. Because those calculators are slightly different than this app.
That was.
That just
very
made
quick.
it so much worse.
Oh,
Look. Is
Hey,
yours
I've
look
got
like a
two.
smashed pancake?
oh my god, wait, it's so cute. Oh, did I take this in right? No. I did a different thing each time. I put in a different
Cool.
That. It's a little wobbly.
What was your window again?
Just gonna make this too.
It's like wobble. Yeah. The T, the RNA doesn't have that. All codons matching.
Yeah. True.
Okay, that's better. How'd you do that? I don't have auto. I just have whatever value is in there.
Yeah.
I don't know.
I'd make it like,
I don't know what that is auto.
well, I would make it like a pi over 12 or a pi over. So far, we doing okay?
Who invented this?
To be honest, I don't know.
Why they invented?
Cause
That's a good reason.
I'm just wondering.
it certainly has lots of applications in fields where you don't have anything straight, which is, you know, as we were talking about last week, everything. Yeah.
You know.
But like when you think about it, like longitude, latitude, all those kinds of things, those are not linear. Those are measured in degrees, yes?
Yeah.
They're all about measuring where a point is relative to the center of the earth.
It's just helpful.
Okay, you guys ready to try another one?
I suppose.
This one's even worse.
No, this one's easier, I think.
No, the printing.
Oh, the,
Oh.
Yeah.
You guys,
It's like just on worse.
sorry. Hey, you guys, when theta is, so let's like start thinking through a table with theta and r. So if theta is equal to 0, according to my equation, what's going to happen here?
0.
Cool, that one's an easy one. Okay, what if theta is equal to 4?
2.
2. What if theta is equal to 6?
3.
Crazy math here.
Okay, what are you guys seeing?
It's 1/2 of the other value.
Okay, so as the angle increases, so does the radius. So start visioning, what would that look like?
An outward spiral.
It would be a,
Fibonacci spiral.
it's not Fibonacci spiral, but it is a spiral.
Yay.
Yes?
Those were the good days.
Okay, you guys, so now these are polar, so it might be easier for us to think of this as pi over 6 and pi over 12. Yes? And pi over 6 is 0.5 and some change, 0.57. Pi over 12 would be 0.25, like pi over, so like it'd be like here.
Oh Lord. I'm just gonna put it at 0.7. That's gonna be great.
And then at pi over 2 would be pi over 4, right? And let's see, pi over 4 is like, yeah.
Oh, I wasn't actually gonna answer the question. I had this other question.
Go ahead and
What
answer
would
it.
be-
Go ahead and ask it.
Will we learn the like equation for the Fibonacci spiral?
No.
That's a little too complex for us. Is it?
I feel like it'd be easier because it's like. It's not all funky.
Does it have an equation?
I'm just so lost on these values.
Now you're making me feel like I have to figure it out.
The Fibonacci sequence.
It's obviously not that. Yes, it is. Because I grabbed my calculator and it looks the exact same.
2 pi would be 3.4.
I remember super knowledge. This is wild. Like, wow.
I think it's pretty cool.
It's pretty cool.
Wait till you see the next one.
Oh god. I should tell my sister that we're going spirals and tell her not to take math.
To take math as a whole.
Well, she's where we are at the time.
All right.
I totally ruined this prize.
Now you're up
For
to
this one?
figure it out.
It's cool, isn't it? It's a cool looking graph.
Well, my window's messed up, so I don't know if
Oh,
I'm
you were
seeing
about
the
to
whole
say that
thing.
you figured out Fibonacci sequence, and I was like, wow. Yeah, you're right. Close enough, right?
I didn't have any extra points for these, well, except for these two, these three.
You might wanna, I'm just saying, you might wanna be careful what you wish for, because we're doing derivatives of these tomorrow. That was pretty funny.
Rats.
Let's start here. You guys, what's my first point? What's my radius of the first point gonna be?
1.
Second point?
Oh, it's,
I need to look at it.
that was pi over 2,
It's
so
root
it's,
2 over 2.
so, wait, no, not pi over 2, sorry.
1
root
minus
2.
root 2.
Yeah, that one.
1 minus the square root of 2.
Yeah. Is that a negative 0.4?
Yes.
Like an airplane?
I'm sorry?
Is it like an airplane?
No.
No.
Wish it was.
All right, so let's see. 0, 1. You guys, pi over 4 negative 0.414 would be here. Everybody good? And then pi over 2 negative 1 would be here because of that negative radius. And then 3 pi over 4 negative 0.414 would be here. Negative 1. But keep in mind, these went in an order, yes?
Oh my god, it's gonna be like a star. Oh.
Sort of.
That's not a function.
It is not a function in terms of x. It is a function in terms of theta. But you can't use the vertical line test to decide if something is a function in terms of theta. But even then, actually, yeah, no. It's a function in terms of theta. You guys, this is not enough. Let's go ahead and do a few more. So let's see, next would become 5 pi over 4. And then we'll do 3 pi over 2. And then 7 pi over 4. And 2 pi. Ooh. Hold on. So then let's see. 5 pi over 4, 2.14 would be here-ish. And then 3 pi over 2, 3. Let me here-ish. Oh, this is off.
It's a heart.
Oh, it should be here. That's fine. And it turns out,
Oh, that's cute.
that there's names to the different polar graphs. This one is called a cardioid.
Oh my god. That's.
Why is the graph not showing the loop?
Because it's not. Actually, that's a good question. Should.
What's wrong?
The graph itself doesn't show the loop.
Yes, it does.
Ours does.
Alright, it's just
Mine
good.
doesn't.
Oh, because it's the thing.
Don't make your X step really high though. I did it. It's still graphic.
Not one. That should not be one.
Point book. Just do the same steps.
No, point. Let's do point one. That's.
Elaine, you're so smart. You're so smart. Mine's still a
So
little bit
that
easier.
Wait, what's your step?
I made mine like really small because I didn't really understand the step at first, and it's taken a minute.
So the step of our current graph is pi over 4. Right? It's how much theta is going up by each time when it does its calculation.
Figured that out once.
We don't have the loop still. Why is it
That messed it up. That made it worse.
Double check you typed the equation correctly.
Oh,
2 seconds.
my bad.
All right, so tomorrow we are going to focus on graphing ones of these called rose curves.
Oh.
We're going to do more graphing of these. I haven't printed the extra practice off yet because I made it during second period. But we're going to get more practice graphing. So we're gonna do more practice graphing at the beginning, okay, with a worksheet that I'm creating. And then we'll do derivatives and stuff of that towards the end of the day tomorrow. Super exciting stuff.